Okay, this is just an offshoot of the last video to explain how to do battery calcs in more depth. So here I'm showing the APS, or the remote power supply number 1 battery calcs, and I'll show you again that the riser diagram is in reference to this remote power supply, right? So we have the battery calcs furnished here on the plan set, and what we want to look at is what that entails, right? So I'll jump over to NFPA 72 to show you what I'm talking about. So the secondary power supply under section 10.6.7 in the 2022 edition says that under the capacity, that the secondary power supply for the protected premises shall operate the system under quiescent loading, which is standby or non-alarm condition, for a minimum of 24 hours, if you can see my cursor here. And then it also has to provide battery power for the system under an alarm condition for a minimum of 5 minutes. You can see that here, right? However, that changes. Let me just drop this capacity drop down. You can see that there's different instances for the capacity based on the type of the system. So like I mentioned, this one is a voice evac system. So it actually has a 15-minute alarm, if you can see on the second row here, instead of the 5 minutes. So just keep that in mind, that if you have a voice evac or a mass notification system, that then you require 15 minutes of alarm instead of the normal 5-minute alarm. But the standby is still 24 hours. So that's what this table indicates. So if I jump back to the plans, you can see that they call out the standby hours here. I'll zoom in a little bit. Standby hours 24 and 15 minutes of alarm because it's voice evac, right? So that's correct for the battery capacity side. Now, what we want to look at is how to actually do this calc, right? It looks kind of weird. You've got some columns this way and some different rows. So you have standby milliamps up here in this column, and then alarm milliamps in this column, right? And if you go row by row, you'll see that they call out the different notification appliance circuits that are referenced by this power supply or the panel. So you've got NAC 1 through NAC 4, and if we can cross-reference that with the riser diagram here again, that you have one notification appliance output, the second one, the third one, and the fourth one, right? So we've got 4 NAC circuits, which is what this shows. You've got NAC 1, 2, 3, 4. And then any other auxiliary loading that's being applied to this power supply is also indicated, right? So what you want to do is take these standby milliamps for everything that's being powered from that supply and sum them in this column. And then you want to do the same thing with the alarm milliamps. So anything that's rated, the alarm rating for each of these circuits, as well as, so all the devices that are on these NAC circuits are already calced in this this number here, right? So you've got all these strobes and horn strobes, and each device has its own alarm rating in the technical data sheets that are provided, and those have already been summed, right? So that's where these milliamps for the alarm are coming from. So you want to sum these rows down in this column, as well as sum these rows down in this column, and at the bottom you can see that there's a total. They call it the total loading right down here as 82 standby milliamps for standby, and then 1,733 milliamps for alarm loading, right? Then once you have both of these numbers, you want to take the total standby milliamp loading and you want to multiply it by the 24 standby hours that are required. And likewise, you want to take the standby or the alarm loading and you want to multiply it by the alarm hours that are required. So we'll take this 15 minutes to convert it into hours. So that's what this is doing. You can see these little equations they've indicated here, that this first one is standby hours times total standby current, and the second one is the alarm minutes divided by 60 to get it into hours times the total alarm current. Okay, so they've taken this 82 here from the total of these rows in the standby column, and they've multiplied it by the 24 standby hours to get this 1,968 total standby amp hours required. Then they take the 1,733 summed column of alarm milliamps, and they've multiplied that by this 15 minutes that has been divided by 60 to get it into hours, and they get a total of 433.25 amp hours. And then we take the total standby and the total alarm currents that we just calculated and add those together. So they took this 1,968 plus this 433.25, and you get 2,401.25 amp hours. Okay, so that's what's required from the system based off of all the devices that they have, like as you can see visually on this riser diagram. So everything that's being powered from these batteries in this, or I'll zoom in a little bit, from these batteries that are located in this power supply, that's what we just calculated, right? This battery calc shows all the standby and all the alarm that's required should this utility power from this dedicated branch circuit fail. So the secondary power that's being provided by these batteries is that number, right? Is the number that we've calculated right here, this 2401.25. However, that's just initially, right? These systems could last for a long time. So the codes bring in a derating factor, which is also a safety factor that's kind of applied to these circuits in case the batteries don't have the same capacity over time. And I'll show you that in the code too. If we go down a little bit further from where we were in the capacity section, it lists a requirement for a derating, right? So let me try to find it here. Here we go. If you go down to section 10.6.7.2.14 star, again in the 2022 edition, it says, as a minimum, battery calculation shall apply a correction factor of 1.25 for aging to ensure the battery can meet its current demand at the end of service life. So that's where this 1.25, let me jump back to the blue beam. So this derating factor of 1.25% is applied to this number. So if you take this value and you multiply it by 1.25% to add an additional 25%, then we get 3,001.563 amp hours. So this is the required capacity for that secondary power supply. And this is in milliamp hours, right? So if we divide this value by 1,000 to get it into amp hours, that's where they're getting this 3, and they're just rounding down because it's in the thousandths place, this 1. So they get 3 amp hours total is required for the system. So you need to have at least that from the batteries that are being output. So they're going to provide 2 7.2 amp hour batteries, which is greater than this required capacity. Okay. And you can see that here that they have 2 12 volt 7 amp hour batteries, and that's greater than the loading that's being applied to that power supply. So that's how you can do battery calcs. And I have this little sheet, which is a little helpful too. I like to think of this is just a different one to show that, say we have this condition. This isn't my image, by the way, no copyright intended, but this is kind of what the rows show, because the other one's not as clear what's being drawn from it. But take this calc, for example. If you have one control unit, so this column shows the quantity of devices that are being applied, and then the standby current amps that are applied to each device and equipment, as well as the alarm current that's being applied to each of these rows. Same with the quantity of those, and the total. This yellow column and the red column show the sum of the current across those devices, right? So in this first row, we have the fire alarm control unit, right? So there's one quantity of that for both standby and alarm. Now the alarm has a little bit more rated capacity than the standby for that device, right? So we've got a 0.1 amps for standby and 0.2 for alarm, and only one device. So one device of standby, so these numbers are multiplied together to get the total for that. Then you've got one quantity times the alarm, you get 0.2 amps for that. Then we go to the next row and you have smoke detectors. So there's 4 smoke detectors, let's just say, for this circuit. So you've got a quantity of 4 and a quantity of 4, so those match. But again, the rating per that specific device is different, right? So their standby amps are a lot less than their alarm amps, right? I mean, that's a 4-fold difference there. So you have to take this quantity, multiply it by, this quantity, multiply it by the rating per device, and you get 4 times 0.001 gives you 0.004. So this is the sum of standby amps for 4 devices, 4 smokes. And then if you take the alarm, you take 4 smokes times 0.05 amps for alarm loading, and you get 0.2 summed current for that, right? So hopefully that makes sense. I'll just use this this marker here. That you take this multiplied by this, that gives you this. Then you take this value multiplied by this, and that gives you this, right? And then dropping to the next row for a horn strobe, they say that there's, say, 10 horn strobes on this circuit, right? So we've got 10 and 10, so those quantities match. Then they're saying that horn strobes don't have any standby, right? Because they don't actuate, only initiating devices would actuate the horn strobe. So it's not being monitored by the panel, right, until it's in an alarm event. So it has 0 standby. So 0 times 10 is 0. Again, multiply this by this, and you get this value. And then jumping over to the alarm side, once the horn strobes are in alarm, though, they're drawing quite a bit of current, right, from the panel. So you can see that it's 0.075 per horn strobe, amps per horn strobe. So you take this value, multiply by 10, because there's 10 horn strobes, so they're all outputting this quantity, you get 0.75 total amps required. Then if you sum the rows down, right, if you sum these rows down, you get this value and this value. So we're going to take 0.1 plus, so you're going to sum these rows down, and you get this quantity here, and you sum these rows on the right, and you get this quantity here in amps. Then again, you take the standby and you multiply it by the required standby time, which in this case is 24 hours, again, like I showed you in the code. Jump over to the code again. Back up under capacity for secondary power supplies, right? Secondary power supply capacity. You are required to have 24 hours of standby. So that's where this 24 is coming from. So you multiply that total standby by 24, which I've done here across this way, and you get this value for total required standby amp hours. And then likewise for the alarm side, you take this summed value for each device that's on that circuit, and you can see this little red arrow down here. They multiply it by 5 minutes of alarm in this case, right? Because this is just an example. It's not related to the plan set. But this 5 minutes from the code, again, is right underneath that one that has a 5-minute loading right here for alarm. Not the quiescent, not the standby loading, but 5 minutes of alarm is required, right? Unless, again, you have a voice evac or a mass notification system, in which case you would have 15 minutes of alarm. But in this case, they only have 5, and that's what this 0.083 value is. So 5 minutes, I'll try to do this quickly, shorthand, divided by 60 equals 0.083. Whoops. Right? So this is, if you have 5 minutes, you can divide by 60 minutes to get it into hours. So that's what this 0.083, which is right here, is saying. That's how many hours are required. So you multiply this value times the summed column for alarm loading, and you get 0.095 amp hours of alarm required. Then, like we did before on this in Bluebeam, right, we add those two different columns together, which is what they've done here. They've added this summation number plus the other one that we just did down here on this row. So we're going across now, where they add these over and they give you a total of 2.59 amp hours for both standby and alarm, right? But then we have to derate those, and you multiply by whatever the derating factor is, which is, in this case, is 1.25, and see, they call it a safety factor. But again, back to the code, it says, whoops, let me close this and try to find it. It says, at a minimum, a correction factor of 1.25, right, for aging. So we multiply that total that we summed by 1.25 to get the actual total value of 3.24 amp hours required. So your batteries have to be greater than this required loading. And yeah, so hopefully that gives you a little synopsis of how to perform battery calcs. And I mean, this can get pretty in depth, right? Maybe I'll do one more, jump back to Bluebeam to show you the fire alarm control panel, because it's got a lot more going on. So we're back on the actual plan set, right? And now we're going to take a look at the control panel itself. So you can see fire alarm control panel. It's got two 12-volt, 35 amp hour batteries that are the secondary power, right? because it has its own utility for its primary power that's coming in, and it's powering everything off of this dedicated 120 volt branch circuit. So that's primary power. If this power fails, power goes out, then the secondary power, these two batteries, shall be sized accordingly to provide 24 hours of standby and 15 minutes of alarm, because we have a voice evac for this specific case, right? And it has to supply this entire circuit, all these circuits that are being supported by that panel. So again, if we jump down to the calcs for the panel itself, it's showing the 24 hours of standby and the 15 minutes of alarm, again from the code under capacity. We've got 24 hours of standby and 15 minutes of alarm for a voice evac. So I'll jump back. That's what those are. Then we've got a bunch of different stuff going on now, right? It's requiring more of a capacity than the remote power supply, right? Which makes sense, because the remote power supply is just an extension of the panel, and it's providing additional support throughout a larger system, right? But the panel itself requires a lot more capacity. So if I zoom in again, the panel, this is the quantities that we were just mentioning in that other example. So there's one of all of these things are being applied to the panel, or the panel is supplying that much, right? So the batteries have to account for all of these components or this equipment. So if we go over to the right, each equipment has a different rating, right, aligned with it. So the standby milliamps, again, in this column, and alarm milliamps in this column. Each device or equipment in each row has a different rating. So the central processor module has 211 milliamps. We'll just jump down here. Control display module with 24 indicators and 12 switches has 8.52 milliamps. Then just keep going down. The paging microphone has 8 milliamps, right? And you can see conversely that in each row, the alarm amperage is higher for a lot of these devices, right? So you've got 101 milliamps instead of 85 for the alarm versus standby. Then you've got like 204 versus 144 for the signature drive controller for that device. So again, we want to sum maybe I can draw on this one too. Here we go. I'll try to draw this. Let's go up here and make this 2, 3, whatever. If you sum down this column all the way to the bottom, you get this total loading, right? Then if you sum this column all the way down to the bottom, you get this loading. So they've done that, and you can do it yourself, right? You can take, in this case, they're all one quantity, but if this value was 2, oh man, this is a big, say you had 2 modem communicators and dialers, right? If this quantity was, oh my gosh, that's massive. Let me change this to 1. Say instead of 1 quantity here, and say, let's just pick another random one. Say this wasn't 1 and this was actually 3, right? Well, then you would take 2 times this value, so it would actually be 120, right? And then 2 times this value to be 180 milliamps instead of 90 and 60. So hopefully that makes sense. So again, if there were 3 audio telephone interface modules instead of 1, then you would have to do it for each device. So if each device had a specific rating, then you would have to sum that per each one. So you would take 3 times this standby and 3 times this alarm, right? So these values would definitely be greater than what they are now. So that's one thing to account for if you're in the planner view side or designing. You have to account for each individual device. So again, they've summed these values down to these totals for each column, right? But then we have to address these ones each individually, right? So you want to take this standby alarm current, and they've just repopulated these boxes one further down. So you want to take the standby current and you want to multiply again by the total standby current that's required, which in this case is 24 hours. So you want to take 773.04 times 24 hours of standby, and you get this value. Then you want to go back to this alarm value, this alarm current, and multiply it by the total alarm hours, which is 15 minutes. So again, if you go down here, we take 15 minutes, divide that by 60, times the total alarm current, which was the 6480, then you get this value here, right? So this is the total alarm in amp hours, and this is the total current in amp hours. Then you want to sum these two together, and you get this value down here. So they've actually incorrectly indicated it right here. This should be a plus sign instead of a division, right? Because you're adding total standby plus the total alarm current to get this value right here. And then you want to take that value and you want to multiply it by the derating factor, which is 25%, right? So when you do that math, you take 20,173.02 times 1.25, you get 25,216.28 amp hours, or milliamp hours. Sorry, everything's still in milliamp hours up until this point. So then you want to take this value, because it's in milliamps, divided by 1,000 milliamps to get it in amps. There we go, divided by 1,000 milliamps. That gives you this value over here, 25.22 in amp hours, right? Which they've indicated here, that it's amp hours. So that means that this is the minimum required design loading for this panel. So you need at least batteries that provide more than this capacity. So they have elected to supply two 26 amp hour batteries, right? And they actually don't show that in the riser diagram. I think there's 35 amp hour batteries. Yeah, they've shown, at least this visual shows two 12 volts, 35 amp hour batteries. So that's one thing to note, that there is a discrepancy, that it has to at least supply the batteries that they've indicated here. But again, this value is greater than this value, and that's what you're checking from a planar view standpoint. And we verified the calcs that is in fact correct based on what they are stating in this this figure here. So hopefully that gives you more of an understanding of battery calcs, and let me know if not anything else you want to see, and potentially I'll jump back into the voltage drop calcs and do that more in depth for you. So thanks.